don't think they like.
I didn't find anything before us people.
Actually,
I
they
call
did.
shenanigans.
How did I
How
get it? How did I get it? I'm guilty. Guarantee it.
By harassing Chad.
Okay, here we go. Here we go. Get out your notes. This is huge. This day is probably the most important day we've ever had in here. No kidding.
This is big enough for the huge.
What about the last 4 most important days?
No, this is a huge day.
This is the biggest day we're going to have in our practice career.
This is our second most important day this week.
Mr. Wade, did you put
Yes.
up the lessons?
If I haven't, I will. I don't know. Yesterday was a bad day.
Yeah, what your shenanigans yesterday was? Yesterday was a great day.
I have my graphing notebook.
Yeah, it was terrible. I got home. There wasn't food ready. I was just so tired.
There's nothing for you. Big size pizza.
My leg.
I made it.
Period is repetitive. I don't even want to.
Those times you know no one's life.
Period is definitely
What is
repetitive.
What is this, 3.2?
No, I made it. And I have 8.
There's only one period.
Mr. Wade, is this new stuff?
Yeah.
Those
3.3.
That big.
No,
I know that, Ron.
Okay, I'm gonna give you some techniques here. Put your no more FaceTime, Shane. Put that away. I know it's hard to put down. Okay, I'm going to give you some absolutely amazing techniques for doing some calculus stuff that you will take with you to college, and you're going to love this. This is good stuff. Right now. Okay, so we're moving on to this is we're preparing for our related rates is kind of a pseudo big topic, but this is the main show for differential calculus is optimization. Okay, and we're taking our first step into optimization today. And you already know the pieces. We have to put them together in a systematic way. So what we want to do is we want to take some function, f of x equals x cubed minus 3/2 x squared in this case. And we're going to analyze this so we can find all the interesting parts. We can find the peaks and the valleys. We'll find, and from that we'll be able to tell the intervals on which the function is increasing or decreasing, all kinds of good stuff. Now here's how we do it. This is something a little bit different than I've done in the past, but I think this makes sense. I'm going to try this out. What I want you to do is to get a piece of graph paper. How about?
I got it.
No. Come on, homie.
Let me get that for you.
Come on, homie.
Thanks, Matt.
Oh, here you go.
Thank you.
What a quiz.
Your quiz.
Oh, that didn't really work. Quips.
So, oh my God, your little quiz.
Thanks.
I swear.
Okay, so here's what we're going to do. We're going to take this thing and we're going to make ourselves a little table here at the bottom.
Right.
So we're going to go.
Better do it right the first time.
It's down here. We're going to make a little table that looks like this. We're going to go.
Yeah. Ooh, straight lines, what?
Bull snipes.
Yeah, you're using the straight line. No. Great observation, Chad. Yeah. Great observation.
Straight line to Elizabeth. Don't you wish you had one?
I just wish I could draw lines that straight.
Okay, so then on this first line,
And I can get you a
this is going to be x. This is going to be y, and that's going to be y prime.
Okay, wait, I don't understand.
Do you want us to
graph
have
like
a
that
graph?
above it?
Well, don't you have graph paper?
Yeah, but I mean, where's our graph
very
gonna go?
Oh, it's going to go. Yeah, leave yourself a little space. Right, you're going to want a little space to do the graph.
Like a quarter page, half page, third page.
I'm going to say about 3/5 of a page.
Okay.
That's crazy, mate.
Shit, what are you just the whole page?
One fifth's not exactly 3/5.
You'll be okay.
3/5 of a page.
My bad. And it goes the whole width of the paper?
Yeah, if I were you, if I had a full page to work with, here's what I would do. I would set it up sort of like this.
They're like this.
Here's where your graphs can.
This is what I did, Coach.
That looks pretty good. Ideally, here's how I think I would do it. I think I'd set it up like this. I think I'd set it up with the original problem up here.
Okay, wait, that's the problem at the top.
What's the squiggle?
Oh, what's the problem?
Wait, I thought it was f of x, not y.
Graph. Do you want us to write
That's
that?
just where it goes. Here's your work. So here's where you're going to do your differentiation. Here's where you're going to have like y equals something, y prime equals something. And then down here at the bottom, here's your little table, right? You got your x's, y's, y primes. This is going to be great. Oh, this is going to be awesome. I think we're going to want to do, yeah, this will be good. This will be good. You want to have, how many in your table? You're going to, the columns, if you want to make them, you can, but you don't really need to. All you really need to do is just this. Okay. And then you really want columns. We're just going to write numbers there.
So you're saving this so we can print this, right?
No. Wait, this is
Yeah.
art class?
Okay.
Yeah.
I signed up for calculus.
Well, okay.
Right. Calculus is art.
All right.
Calculus is not art.
Okay, so here's our problem. So x cubed minus 3/2 x squared. Now, in order for us to analyze this, we want to know, we're going to have to do a derivative. So let's go ahead and get that out of the way. What's y prime?
3x. Everyone's life.
Okay, everybody good at that? Power rule? Okay, so we want to know then, in our table, we want to know, first of all, are there any places where the function is ill-behaved? Are there any asymptotes or things like that? So we're going to look at the original function, and we're going to ask ourselves, and this doesn't really play a big part in 3.3, but it does in like 3.6. And so we're going to start talking about it now. When we want to do a complete functional analysis, we got to know where vertical asymptotes are. We're eventually going to talk here soon, section 3.5. We're going to talk about horizontal asymptotes and slant asymptotes. We're going to want to know where those are. We're going to write all that stuff down. We're going to want to know if there are, we want to know what the skeleton of the function is. Are there any kind of weird asymptotes that are going to frame the function? Hey, quiet! Hey, shh!
Big day, you guys.
Good day.
In this case, there aren't any, though, are there? This is, if we look at the function y equals x cubed minus 3/2 x squared, there's no problems. No roots, so we don't have to worry about taking an even root of a negative number. We're fine there. No x is in the denominator, so there's no chance of dividing by 0, right? So we're fine. What about the first derivative? Now we want to analyze the first derivative for our critical numbers. Question?
What is it?
We're going to just analyze this thing. When we're done, we'll talk about what we've got and what we can do with it. So we want to find, we want to know where we get peaks and valleys. Eventually, we're going to look at things like horizontal asymptotes. We're not going to get to that today. We'll add that piece a little bit later. I really don't want people talking right now. This is very disruptive. Please don't. Today, we're focusing on just topological features. We want to know where we get relative extrema. We'll know how to find something called an inflection point soon. We're not really getting to that today. We'll add that little piece. But we just want to know, with a rough sketch of this thing, we can tell a lot of information about the function. Peaks and valleys are huge. When we're looking at the real purpose of calculus is typically, differential calculus is to figure out what conditions are going to optimize something. Maybe it's profits, maybe it's, who knows. But we're graphing some dependent variable, some function, as a function of some independent variable. So maybe it's profits as a function of items sold, or it's temperature as a function of time, or it's something like that. Something interesting that we want to know, where is it going to be at its greatest value, where is it going to be at its least value, when is it increasing the most rapidly, when have we hit the point where it's increasing but less rapidly, so we can anticipate that we're going to peak, sales are going to peak. So when we start looking at things like that, like complex economics, we look at analytic economics, this is the kind of thing we would be really interested in knowing about. Now, there are some tools, of course, now, graphing calculators and using computer algebra systems that'll do a lot of this for us, but you can't really use this stuff well until you know what the calculus is all about. You can use the analytic tools, but only after you have a clue, what they're doing. So let's look at this one. Let's go in search of critical numbers. We got two kinds of critical numbers, right? Where do the critical numbers occur? When the derivative is undefined or equal to 0. Okay? So are there any places where our derivative is going to be undefined?
No.
No, there aren't. And in fact, here's some language that you can take with you. When you have a polynomial like this, right? Polynomials are, the mathematical term is well behaved. There is no place in a polynomial where it could possibly have a vertical asymptote or do something wacky like that. They don't have any sharp corners. They're smooth. They're continuous everywhere. And the nice thing about polynomials is when you differentiate polynomials, you're just going to get smaller polynomials by the power rule, right? The constants, if I had a constant here in my polynomial, when I differentiate that, it goes away. But every other term in the polynomial, the power just drops by 1. So if it started off as a 4th degree polynomial, I'm going to get back some 3rd degree polynomial. All right. There we go. Good. Okay, so there's no place where the derivative is undefined, but where does it equal 0? Well, let's find out. If we set this equal to 0, 3x squared minus 3x equals 0, we just have a little algebra problem to do. So what do we do how do we solve that algebra?
At 3x. Divide by 3.
Yeah, we'll just, hold it. No.
What do you mean no?
No, we've got an equation in standard form. I can't isolate x here because I have two different.
Factor.
I got a factor. Right. So what do I always, when I'm factoring, factor out a 3x. I want to factor out the greatest common factor. So I can pull out a 3x, leaving me with, I could, but this is much easier. Right? We'd rather avoid the quadratic formula if there's an easier alternative. What am I left with if I pull out a 3x from each term? X minus 1. Okay, so my solutions are then either x equals 1 or 0. Sure, I've got the factor 3x. 3x equals 0 when x is 0. X minus 1 equals 0 when x is 1, right? Okay, so now those are our two critical numbers. Those are potential relative extrema. Maybe not, maybe, right? Now, previous to this, in section 3.1, probably not 3.2, but in 3.1, you guys looked for absolute extrema, right? And Math Excel sometimes kind of twists this around a little bit. They had you find relative extrema also, and the way you did that was plausible but not great. It's not efficient. They had you just take all the critical numbers and evaluate the function at those critical numbers. Now that's okay, but we're going to look at a much better technique today called the first derivative test, which is a way better way to do it. So we're going to take these critical numbers and put them on our table. Okay, so we're going to go, and now notice here, I've got this thing set up, so let's go ahead and go by, this is sort of experimental, but we'll see how this goes. Let's go by, there's 1, or there's 0. How about here's 1, there's 2, right? So we're going to go by 3s on this graph, so we can spread it out a little bit.
So I'm writing a pen, so this is the only graph I have.
This is fine. This is fine. So then down here,
It actually makes 3, or is that 1?
well, that's 1 and that's 2.
Okay.
That's -1 and -2.
I'll make my graph.
Okay, so then down here at x equals 0, let's put a 0. Okay, that's an interesting place. That's a critical number. I'm going to do mine in green because my critical numbers were green. So there's 1, and then we had one at 1. Whoops, we had one at 1.
Oh, there you go. Messing up again.
I actually, as a matter of fact, have a video.
Those are the x values. Okay. Now we don't really necessarily at this point need the y values. That's okay. We'll get to that. What's nice about this is if I put in a y value, if we evaluate the function, for example, at 0, I'm just getting back what? 0. Okay. So then if I write in here 0 for y, that constitutes an ordered pair, just seen sideways, right? So 0, 0. There are the coordinates of that point. So if I want to, I can go ahead and put a point right there that I know the function travels through. That helps me anchor the function. We could do that for all those points, but we don't need to. That's if we want to, we can. But the important place to work here, the rule is when you're making a table like this, and I've always done mine in the past, just so you know this is a little different for me. I've always thought this was far and away the best, and maybe it is. Maybe I'm wrong in trying this. We're going to try it anyway. I think there's some sense to this. I've always made my tables like this in the past. And that, which is nice in the sense that ordered pairs show up as ordered pairs, but I think sometimes people have a little bit of trouble mapping this column onto the x-axis. It's not natural. So I'm going to try this horizontally aligned. The advantage being that now when we write these numbers, they actually correspond to the x values on the real line, on the x-axis. Okay. Now the rule is then we want to work, when we're doing calculus, we want to work as far down the table as possible. It's more efficient to work with the first derivative than it is to work with the function. Soon, in next section, when we introduce the second derivative, we're going to want to work down in the second derivative row whenever it's practical to do that. And we'll get there when we get there. But for now, this is where we're stopping. But this is the important row. Okay, that's where we want to be. So we knew that at these critical numbers, the reason they were critical numbers, and we can recognize this in our table now, is that when x was 0, y prime was 0. That says to us critical number, right? When x was 1, y prime was 0, so there's another critical number, right? Those are the places where maybe the function is going through a turning point. Because now think what it means topologically to be a minimum or a maximum.
How do you know what the y was?
Say it again.
I didn't know y was used.
Because I plug it into the function.
Oh.
That's it. We're just evaluating the function at those x values if we want to know what the y value is. Okay. Now we may or may not even care about that. Think though what we mean when we talk about a peak or a value, relative maximum. A relative maximum
Points around.
could either look like this or it could look like that, right?
Yeah, but that one, it doesn't have the, it has the cusp, so it doesn't have a.
Yeah, what is
Yeah, just like
Okay, but they're both relative extrema, because an ant could stand right here and be on top of a peak, look around and be higher than his immediate surroundings. Same thing here. These are both examples of what a relative minimum could look like, right? Now, what's happening with regard to the derivative? As an ant moves through, walks up the slope, gets to the top, and then walks down this side. When we say it's a turning point, what do we mean? Well, it's changing direction. What's that imply about the values of the derivative?
They start going down.
Okay, they start positive, right? On the red, when he's walking up the slope from left to right, you can see that the slope is positive. So we could divide this up. We've got this part over here where the derivative is positive, right? And this part over here where it's negative. Same thing here. It's not a smooth transition, but we're still moving from an increasing function. And when I say increasing function, that just means positive slope, right? Increasing function to a decreasing function. So that's the signature. That's the first derivative signature of a peak. It's a place where we're transitioning from positive to negative slope. That has to mean relative maximum or peak, doesn't it? That's what it means. Now, if the function is undefined there, it could be doing something weird where it's separated, but we've already found those places. So assuming this isn't some weird break in the function, which we already would have known about, it has to be a peak, right? Okay? Yes?
Can a cusp be a relative maximum minimum?
Yeah, that's a cusp right there.
Yeah. Okay.
What was that thing then?
The other day you said that.
Yeah.
What did I say?
You said the exact same
Oh, maybe it's
situation.
an extreme value. Yeah,
let's see.
extreme value of a trust.
Shoot. Forgot.
No, a cusp.
Absolute. Can't have an absolute max.
You said it's undefined.
There was something you couldn't have on cusp.
You can't. Okay, no. What you asked me was if an infinite asymptote could be a maximum, right?
No,
I
I'm talking about when
said
it has a
cusp.
sharp.
Didn't say anything about asymptotes.
You guys. Well, the question I remember the one you asked me was, we were talking about if something went way up. If it approached infinity, if we had an asymptote, and that can't be. But a cusp can be.
Okay.
Because, and now think why? Because the first derivative, the two places where the derivative, where we could have a peak or a valley would be places where we had a horizontal tangent or we had a sharp corner. This defines one of the two kinds of potential outcomes of a critical number. right? It could be like this if the derivative is undefined. It doesn't have to be. It might be like this. It might just be that the function's doing that kind of a thing, where it doesn't actually, it's not a peak or a valley, but it's a sharp corner, right? See what I'm saying? But a sharp corner,
It's a critical number at a sharp corner.
Right.
It's undefined.
right. A critical number is a place, that's a potential spot where we could get a relative max or a relative min. We got to check them and see. If it is a relative maximum, that's going to be when the derivative is transitioning from increasing to decreasing, from a positive value to a negative value, right? Okay, now what about the relative minimum?
It's going from negative to positive.
Yeah, it's going from decreasing to increasing, right?
Yeah.
Either way, either if it's a smooth, horizontal tangent type of valley, or if it's a sharp valley and it's an undefined derivative type of valley, a cusp. Either way, that's what it means to be a valley. Okay, so let's go back here to our problem and let's analyze this thing and see what's going on. So we need to know now if we could find some values of the derivative on either side of these two transitions, we'll know what's going on, right? So for example, if I pick a test point, that's what we're going to call this, it's a test point, between 0 and 1, like let's pick 1/2. Okay? All I need to know here, this is what's nice about this. This is why we want to work as far down the table as we can. I do not need specific values. I just need signs, positive or negative. So if I go back to my derivative function, which is right here, it's factored, isn't it? Let's use the factors one. That's the easiest one to work with. So if f prime of x equals 3x times x minus 1. If I evaluate that at 1/2, watch what we can do. F prime of 1/2 equals. Is the factor 3x positive or negative when x is 1/2? Positive. So we'll just take that to be some positive factor. Don't care what it is. X minus 1 is negative. A positive times a negative yields a negative. Right? So we know we've got a decreasing function in between those two critical numbers.
Absolutely.
Now, keeping in mind, and this is really important to get, keeping in mind that the only places where the function can turn are at critical numbers. They won't all work, but there's no possibility of ever finding another peak or valley any place other than those two places, right? And so, are we in danger? If I pick some test point to the left of 0, let's say I pick something like negative 1,000, am I in jeopardy of having, and I find out the sign of the derivative, could there have been, maybe I went too far left, maybe at negative 1 it was a different sign than negative 1,000. Is that possible? No. How come?
Because those are the only two.
Because the only way that it could have changed sign between negative 1,000 and 0 would have been if it had gone through a peak or a valley, and there aren't any, right? So what you know then is that between these boundaries, I've carved this thing up at 0 and at 1, to the left of 0, the behavior of the derivative is completely consistent. It's never going to change. It's either always positive or always negative. If it changed, it would have meant there's another critical number and another boundary, right? To the right of 1, it's always consistent, and between the two, it's always consistent. Now, things get a little messed up. I'll interject this now. We'll talk more about it later. If we had a vertical asymptote in there, then all bets are off. The vertical asymptote divides the function up into separate realms where, anything can happen. So then we'd have to, let's just say hypothetically, that we had a vertical asymptote at x equals 5. Okay? The way we're going to write that is, I'm going to have you guys just do something like this. So we know that's a vertical asymptote. Okay? And then we'd have to say, okay, now the behavior of the derivative between 1 and 5 is fixed. It can't change. But then once we get this vertical asymptote in there, things could change. We have to test a point on this side also, because that interrupts the behavior. Okay? And we'll do a lot more of that later, just so you're aware.
What's the minus between the zeros?
That just means
It's gonna be negative.
the derivative is negative. We evaluated the derivative function at 1/2, and we don't care what the value is. We really don't care. But we just want to know what the sign is. The first factor was positive, the second factor was negative. The easiest way to evaluate the sign of the derivative is to use the factored form. If I go back up here, to this polynomial form, that's kind of hard. Then I actually do have to plug in 1/2 and see what I get, right?
So positive times negative.
Positive times negative, right?
Yep.
Now the nice thing about this is, we've already done this work, because at this point in finding the critical numbers, we've factored it presumably. In most cases, we will have already factored it, and so we've put the derivative into a form that's useful for us, right? So for finding its sign. So we're just going to reuse that work we've already done. Okay. Now let's find the other. Let's go down and find the other test points and see what's going on. So let's pick another test point to the right of 1. It doesn't matter. And we could pick something like 2 is fine. So if we pick a test point at 2, and we go up here and try f prime of 2, what am I going to get? Positive times, which is positive. Okay? And if we go down to -1, let's say. If I put -1 in, f prime of -1 would give us negative times, say it again? Yeah, we'll see that in a second, but we'll get negative times, which is positive. Okay, so then this is positive. Okay, so now Ethan, what's it doing?
Going up and down, up going through 0, then down, and then up.
Right, and look where we can draw that, right here. If it's increasing to decreasing, we know what that shape is. Now I got a 0 derivative, so we know it's smooth. We know that shape, whoops. We know that shape is like that, don't we? Right? That's really handy. So we know that's what's going on at this point. Right here, we're going from negative to positive through a 0 derivative. So it's not a spiky one, it's a smooth one. It's a horizontal tangent. So we know it looks like that.
If it's spiky, that means that it's undefined.
Why does that?
If it's right now, if we knew, so now if this had been, what if the first derivative were undefined here and it were a point of transition? Then it would have been a V-shaped. See? Isn't this cool? So you know what you're doing. This is just going to give us a basic sketch of the graph. Right? We know that if we want to get this thing accurate, we could figure out what the y value is at 1, for example. So what is the y value at 1? Let's see, we get...
Or are we just doing this to sketch it?
Yeah. But then we can answer lots of questions about it. It's going to be 1 minus 3/2, right, at x equals 1. So negative 1/2. Okay, so negative 1/2. So there's a point. And now we can go plot that point up here. Let's see, it's right about there. And now we know what the curve looks like, right? We know that it's doing this. That's a basic sketch of our function. Now the things that you're going to be asked about is you're going to be asked to find relative extrema. Well, we've got a relative maximum at 0, 0. We've got a relative minimum at 1, negative 3/2.
3/2.
Or negative 1/2, sorry. Negative 1/2.
Okay.
Okay, we want to know, for example, the intervals on which the function is increasing. So the intervals on where is it increasing?
Negative infinity to 0 and 1 to infinity.
It's increasing on, good. It's going to increase on
Parentheses.
that interval. Now, what's that say, right?
Bracket?
No, because at 0, it's neither increasing nor decreasing, right? Does that make sense? So every point up to 0. So for all values of x less than 0, the function is increasing, which means I can either go comma or I can do my little, right?
Would it be a U?
Not
sideways U? Or?
It's going to be a U.
Okay.
Yeah.
Ukulele.
Why 0? Wouldn't it be 1?
No, it's 1. You're right.
Okay.
1. Right. So there's the interval on which the function is increasing. Intervals, right? Where is it decreasing? F of x decreases on
0 to 1.
0 to 1, right?
And that's it. No other things.
Yeah, how about that? Okay. Seriously, that's really cool that we can do that.
Is that called optimization?
That's, well, kind of. I mean, we're getting there.
What's this all kind of?
This is if I had to title today's discussion, I would say this is the first derivative test. What we just did there is by testing points around the critical numbers, we can tell if they're minimum or maximum. Okay, that's called the first derivative test.
This is the most important.
It is far away, far and away. Yeah, this is
Is
big.
it more important than anything we'll learn too?
No. But for now, it is. Okay, let's try another one.
What about the other subjects?
Oh, come on. Physics, I mean, yeah. No, I'm kidding. They're all important. They're all equally important. Okay, let's try.
Super feature.
Let's try this one. Let's do.
Okay, so is this still the big stuff, or is it?
Yes.
So same graph paper.
New problem. Yeah, new problem. Flip it over.
We get along. We joke also. Oh, he'll rip me. I know, that's why I don't like talking.
Okay, let's go. Right here. Try that. No. Try that.
So we're gonna have to use a chain rule.
Yes, you are. Differentiate away, please. Yes, sir.
More than 5 minutes.
Okay, so differentiate. So what do we do to differentiate this?
2/3 parenthesis.
Good. Outer layer is a power, right? So we got 2/3 times hand to the 1/3, or to negative 1/3, right?
Yep. Plus. Question mark.
And that's an x squared minus 4. Okay, now what?
Plus.
Not plus.
Times.
Looking inside, the derivative of the next layer is what?
2x.
2x. Yeah.
So multiply.
Right. All the links in the chain are multiplied. They're products. They're factors. So we end up with, then, if we write this as a quotient, we're going to get on the top, we're going to get what? 2 times 2 is 4. 4x on the top. Everybody agree? Right? Because this goes to the bottom. It's a negative exponent, so that's all going down to the bottom.
Oh, okay.
I'm left with a 2 times 2x, so 4x on the top. In the bottom, I'm going to get a 3 times the quantity x squared minus 4 to the negative 1/3, right? Okay. So there's our derivative.
Yeah, positive one.
Yeah.
Not negative one.
Positive.
Ah, positive. You're right. I was just checking to see if you're really paying attention, and you were.
We are.
That's good stuff. Okay, we can do
Yeah, I
it.
wish I had an eraser for my pen.
I bet you do. Okay, so now we want to find the critical numbers. Let's find the places, and let's divide this up. Let's do the easy part. Let's find where f prime equals 0, right? So if we set this equal to 0 now, where is a fraction equal to 0? When the top is 0. So we know that f prime of x equals 0
So when it's 0,
when the top
it's 0.
4x equals 0. So the answer is at x equals 0. There's a critical number.
Oh, wait a minute.
Okay, now let's find the second kind of critical number. We want to know where is f prime
Undefined.
is undefined. When what? When the bottom is 0. And in the bottom, the only part that we're really concerned about is this factor inside, right? Because we know that the only way the bottom can go to 0 is when that factor goes to 0, right?
Minus doesn't work, so it doesn't really.
Make sense?
Yes.
Okay. So that's what we got. So we're going to answer that question. When is x squared minus 4 equal to 0? How do we solve that one?
Plus or minus.
Yeah, we're just going to isolate the f. Good. So x squared equals 4, so x equals plus or minus 2. Okay, so those are my other kinds of critical numbers, right? Good. So now let's put these on our table. I'm going to make a table down here.
So
So we got x, f of x, f prime of x, right? So the x values that were interesting were at 0. We're going to go by 2's this time. So there's
Y prime?
okay. So at 0, we had a derivative that was equal to 0, right?
Plus or minus 2.
Okay, and at positive 2, we had an undefined,
Okay.
and at negative 2,
Why do you put the negative? Why you put the negative 2 on there?
oh, wrong line. Gosh darn it. And I'm just stupid.
Shenanigans.
All right, so
Negative 2 also.
okay, so now we got to know what's going on there. Are there any places in the original function, by the way? I guess we should look at that where it's ill-behaved.
No.
No, because here's what, and this is important. This is one you could easily overlook. This is an odd root because the denominator is odd, right?
Okay.
So we don't have to worry about that rule of
Even root of a negative number.
even root of a negative number. There are no x's in the denominator, so we can't divide by 0 ever. We're fine.
Less than negative.
So now let's go ahead and analyze the behavior of the first derivative at some test points. Let's pick test points. How about at 1, negative 1, 3, and negative 3? We'll just see what's happening there. At 1, if we look at the first derivative, there it is, when x equals 1, and I'm going to write this right here. So f prime of 1 equals, what's that going to look like? The top is, so positive or negative? Positive. Divided by. When x is 1, what do we get there? Negative. Cube root of negative is negative. Right? So this is negative. Whoops, negative. Wrong spot. Right? Let's real quick just do 3 so we can get one of these done. If I plug in 3.
To be continued.
To be continued.